I would like to thank the organizers for having me here. And I promise not to disappoint on the optimist versus pessimist roller coaster of today. So I'll take you through the optimist and pessimist story of how quantum system certification and characterization works. So I've been on the both sides of optimism and pessimism. I'm trying to get the new way of it working, and what makes me optimistic is that in the beginning it was a very like family kind of an endeavor. It was only myself and Nikolai Miklin working on this stuff, and now you see more names on the slide. So we have more people on board of doing things hopefully in the correct way. So I want to give also shout out to Lucas. He has a poster also about this topic, so please go talk to him if you have more questions. And there are some of the theories and experimentalists also coming up on this work. So let me start with the motivation, quantum computers. And if you Google quantum computers, you will see the following beautiful numbers if you sort them according to the fidelity. And I want to ask you honestly if you trust these numbers. So, well, you can blame experimentalists, but I'm also an optimist that experiments have been developing pretty well. And I want to take the approach of saying that maybe we have to improve the theory in order to trust these numbers even more. Let me tell you what's happening at the moment. How are these devices benchmarked or tested? So you will see names like randomized benchmarking if you open their documents of how they actually check their devices. You will see randomized benchmarking. You go on and look at IBM, again, well-established way to benchmark quantum computers called randomized benchmarking. And there have been amazing works done into this direction, many different flavors that people have been using. But also, there are some other results which tell you that actually, if you do randomized benchmarking and try to connect it to this figure of merits, then this is very complicated. And it's not that it's complicated in practice, it's actually quite hard in theory to connect these things together. So if you want to look at these random circuits on your architecture and gather some data out of it, and then produce another random number, which will be gate fidelity, that's pretty much, in my opinion, connected to many times what's happening for the realistic experiments. So some of these numbers reported are quite over-optimistic. But then you can still ask, why do people use RB? Well, one immediate answer that you can come to is that every time you want to test the gate, from a theory perspective, that's what you do, right? You initialize the quantum state, you act with the gate that you want it to do, and then you do the measurement. But also, you will notice immediately that gates and also state preparation and measurements, these are faulty. So these are called spam errors, and these are the errors if you trust your state preparation and measurement, and if you do the process tomography, these errors will inevitably be systematically propagated to your estimate of the gate. And you don't want to do that. And randomized benchmarking is clearly the method which doesn't have dependence on spam preparation. So what is the problem with that? If it's spam robust, what's the problem? So let's come to the testing. What do you want from any good test? And unfortunately, all of us have become very good at testing in the past few years, right? So we have learned how to test ourselves and which tests have which confidence and things like this. But from any good test, you want two things. So let's take two different hypotheses. First is that the fidelity of the implemented gates are bad, and the second that fidelity is good. The first thing that you want the completeness. That if the fidelity is good, then you want the test to say, yes, you're doing well. Well, you don't have COVID if you don't have COVID. You want it to tell you that result. But what about the other way around? Well, if your implementation is bad, you want tests to reject your implementation. So if you do have COVID, you want the test to tell you that. One does not simply imply another. So if you use the test which has only one of them, That's a bad result. And RB is actually only complete. It is not sound. So now you can ask me, what does this mean? Does this cause problems? Well, I don't know. Have you bought time on quantum computing device and ran that? In my opinion, it does cause some problems. But let's look at some other methods. RB is just a warm-up. I have problems with other methods too. So there is a process tomography, which is clearly impractical if you want to do it for many qubits. And we already talked about spam, so it's not spam-free. Then there is gate-set tomography, which is also impractical, and it's spam-free, but it's not sound. Many people disagree on that. So if you disagree, please come and talk to me, because that's very important. I am actually writing an ERC grant on this stuff, and deadline is in a week, so I'm shaping my reasoning there. So if you are against of what I'm going to say in the next slides, you might save a few months of my work. So please come and talk to me. And then there is a last one, which is the self-testing. Self-testing is spam-free and sound, and also computational self-testing with the computational assumptions. But we can agree that at the moment, for a single device, this is not really practical. People have tried to run Bell test on an IBM device, but then they discovered that there was actually signaling on their data. So even, you cannot really do this. Okay, so let me tell you a couple of words about GST. What does GST do? It's a well-established thing. It gives you more data than randomized benchmarking. And a lot of people use it, and they spend a lot of samples, right? It's as expensive as the tomography. What it does, you have a quantum computer in some white box or a black box. It's up to you. You run certain experiment on it, which is some vectorized, mathematically corresponding to some vectorized states. You apply some channels, and you get some data from it. And then GST workflow, without getting too much details, this is not too important, except for looking at this very first line here. Imagine that this is the super operator representation of the channels that you are implementing. You are going to learn this up to the probabilities according to probabilities that you observed, up to some invertible transformation. Now, what is this invertible transformation? It is something that we call gauge. Now, what this gauge tells you is that there are a bunch of other experiments compatible to exactly the same data. Now, this is not surprising. And this invertible gauge, it's something in this super operator space. So what it corresponds to on the level of the channels and quantum operations in the given Hilbert space, we don't know. And what it means, on the other hand, it gives you equivalent implementations which are not even quantum mechanically justified. So far so good. What that people do, they take this results and they report quality metrics which are optimized under this gauge transformation. So what it means is that every time you look at this data, which is obtained by GST, people tell you that your fidelity of your gates is 99.99%, but what they do, they take the reconstructed experiment and they report the best out of all of them. And that could be a problem because sometimes this number can be greater than 1. Well, it's greater than 1. They scratch probably their head and they say, wow, okay, probably our gauge was too much, so let's collect more data. So now you can say, okay, you're being very picky, but I'll tell you where the problems could come in here. The gauge gets larger, noisier your implementation. So what it means is that more noisier your data or the implementation is, more degree you are allowing yourself to optimize over, so possibly more optimistic you will be. And the second is, this could cause systematic errors, because now once you optimize over this gauge, you get the quality of states, you get the quality of measurements. And you tell an experimentalist, you have the gates up to 10 to the power minus 3, but spam error up to -2. And then they go and improve their quality of SPAM, state preparation and measurement. This will decrease the allowed gauge, and next they run the experiment. Because the gauge optimization is more restrictive, they're going to actually find that their gates are now worse. So this creates certain issues into pretty much the workflow of how experimentalists need to improve their apparatus. Now, I'm not the first one who has acknowledged this. This is the screenshot from one of the review papers, which says that a common and fundamental objection to GST and gauge optimization goes something like this. Intentionally seeking out and constructing the gate set closest to the desired targets seems like cheating. It is, if not actively circular. No truly satisfactory answer to this can exist in the absence of privileged reference frame. Gauge invariant metrics have limited meaning and shouldn't be computed. I don't agree with this. I think we can improve things without just doing this thing over here. Gauge optimization is fundamentally a hack, but the quantum computing community has been reluctant to abandon metrics like process fidelity, diamond distance, trace distance, and they are deeply rooted in literature of quantum information, not least because no good alternative has been known yet. And here is a key word that I want to focus on today. Yes?
So doesn't that give you an upper bound at least on the fidelity?
Yes.
So it still gives you something, right?
So it gives you upper bound for the given figure of merit. Yes. Yeah. It gives you something. But usually you want also lower bounds. Yes. Yes. Good. And again, so today I'm going to be talking about this one, trying to convince you that there is a way forward. So let me get to the starting point of my talk. So this is going to be a shorter part because I feel a bit ashamed of just trashing everybody else's work and telling you that this is now a good way, but I hope you'll be one of the person getting on board and at least recognizing that there is, if you don't like our methods, that's fine, but please do recognize that there is a problem in the reporting community of how we report our benchmarks. So what do you want from the certification method or the characterization, any of the quality check methods? That you have a classical user who talks to a quantum server, sends some classical data, gets classical data, and from these learns what's going on. Now, what we need to do, we need to identify short sequences or small set of quizzes or tests we need to send to a quantum computer, which is informative enough that we don't have to run the full tomography, and we can gain certain information about a quantum computer. And that's what we are doing pretty much. We are coming up with certain deterministic sequences that user can send to a quantum computer. It is of the various lengths, and then it can look something very pretty and simple. We can consider a very small example of user just sending single alphabet, let's say S string, and then quantum computer needs to do something there and report the answer. And the key here is that you should require a quantum computer to send an answer 0 or yes if you send the following length sequences, and no if you send those. So very simple test. So this test is known under the name of the promise problem, and this is designed long time ago now by Ambainis and collaborators. They worked on promise problems. And the advantage in promise problems that you have is that it's been recognized that quantum computer can do it with a dimension advantage. So one classical computer would need a dimension that grows exponentially for the certain promise problems. Quantum computer often can do things with a qubit. And then what you can do, you can assume that you have a qubit in your system, send these quizzes to a quantum computer, and the way it will recognize the answer, you want to learn from the answer something. Let's see what the quantum strategy is. You can easily probably recognize the quantum strategy to solve this problem is to start in plus state, apply S gates every time you send the S sequence, and if you send the S gates with 2 times K repetition, where k is even number, then you will get the answer plus. If you send the odd times, it will flip to minus, it will get the answer minus. And this is the quantum model solving this problem for an S gate. You can ask, are there other strategies? And the answer is directly yes. You can solve exactly the same thing with 0, square root of x, and computational basis. But you can immediately notice that these two things, they are equivalent under unitary gauge, which is change of basis, which is the same thing. So you can just rotate your Bloch sphere. This doesn't change anything. And then you can ask the question, are there any other strategies passing this test? And the answer is no, and that's what gives you soundness. So in a qubit, there is no other strategy which will solve this problem. And luckily, actually, you don't need to go very high up in K. You can just use these three tests. And now what you can do, you can take this idea and you can turn it into a, we call it QSQ, quantum system quizzing. You can quiz a quantum computer. You can choose a promise problem, number of samples, according to which you want to test your quantum computer, and you can sample one of the strings randomly. And if the computer gives you a wrong answer, you can reject the implementation. And now the idea and the challenge is to come up with the promise problems, and that's what Lucas' poster is about. This is connected to finite automata theory in computer science, and you want to prove that passing this test gives you soundness. That's an idea. Now, let me quickly go through here very fast. So this is just drawing exactly the same thing as we had before in more quantum mechanical sense. These are the quizzes you are sending. You don't assume anything at all. So it's about, this is semi-device independent scenario. You're only assuming the dimension. And what happens here is that you have a target model that you want to test. You want to certify that you have this model, and you have the implemented model. And now you are saying that it's easy to recognize that if the target model is equal to the implemented model, your test will always be passed. That's a completeness, but that's not what you want. I mean, you do want that, but that comes for free. But you want the other way around. You want to show that if the distance between these two is lower bounded by some epsilon, then your passing probability will be upper bounded. And that's what you would want, because that's what you see in your experiment. You see that your passing probability is lower bounded by some number, and from here you want to do the inference. I mean, I think that's pretty clear for at least our community. So differently, let me put it this way. If your passing probability is greater than 1 minus epsilon, you want to show that there exists a gauge, which is a unitary gauge, which is just changing the basis, computational basis, to something else, such that average gate fidelity is lower bounded by some number. Let me tell you now the results. This needs a proof, of course. Let me quickly get to the technical results that we have. I will start from the single qubit model and the test that you have already seen. So if you have this single qubit model and you notice that your passing probability is 1 minus epsilon, you can test it, send it to a robust certification method in the following way, that you can prove that the completeness, that average gate fidelity for the implemented channel with the target one will be upper bounded by the following quantity, which is linear in epsilon. And what's more important, it will be lower bounded by the following number. And we do have estimates of this number. If it's a very high number and you get a negative number, that's also not good. But you can estimate this number. It's actually not so bad. C2 here is equal to 1. You can do numerical tests. So we have tested around, now this is less points, but around 500 million points. And you can optimize the fidelity. You can look at what is the fidelity with the failing probability. And this slope will tell you that if no quantum model sits on this side, then it will tell you how bad your estimate is of this C2. Now, one can go ahead and do the sample complexity analysis, which will tell you that the number of samples you would need to run in order to estimate or certify the fidelity device independently, it grows inverse proportionally linearly to this epsilon number, which is the best you can hope to have. So next thing that I can tell you about, we have set up experiments in the near to Darmstadt. There is an ion trap experiment from the Ferdinand Schmidt-Kaller's group, and we have certified that his single qubit gates have at least this fidelity. Now, this is at least, of course. And now, this error is usually dominated by spam errors. His spam errors is in the range 10 to -3. We believe his gates are better, but because we are doing self-consistent certification, these spam errors propagate to the gate errors. Let me quickly come to more than 1 qubits. Obviously, you want to scale this to more qubits. So one thing that we assume, again, we assume the dimension only. We don't assume the addressability between the qubits. This is something you need to learn. You assume that you have 4-dimensional system, but when you press one button, you don't assume that it's implementing something on the first qubit and something on the second qubit. You need to learn this. You need to learn your crosstalk. And this is precisely what's depicted here. We assume that every button press can be implementing pretty much a 4-dimensional channel. And here we have no robustness results yet. We have heavy numerical computations, but we have theoretical proofs for the soundness for n-qubit S-gate model, which means that we can certify this for now. You can imagine the n-qubit generalization. On top of that, you can build the certification of the Clifford circuit. And finally, of course, you want to have the certification of universal gate set. And what happens to the scaling? So scaling for the S-gate model for 2 qubits doesn't get so much worse. You still have the linear scaling in the epsilon imprecision. And actually, when you start to increase the number of qubits, you have to make more tests. That means you need to get more information. And this scaling actually gets better with time, which is with a number of qubits, which is something which is, I think, something to be proud of, to not have very badly scalable tests. But of course, number of tests themselves increase exponentially because there is no free lunch. You need to test things oftentimes. So this current experiment we are running at the moment on Quantinuum's H1 model, which they have very nicely compatible experimental apparatus. They have the gate zones where they anyways cannot implement tensor-product of 2 S-gates. Every time they want to implement a local unitary, what they have to do, they have to shuttle 1 qubit in the center and do some gate on the first qubit, and then second qubit needs to wait. And when they have to implement something on the second qubit, they have to shuttle it back, implement something here. So our tests need exactly that, because every button press needs to be something new. And we are going to report these results hopefully very soon also. Yeah. I hope this was a bit more optimistic take on certification, but let me come to the conclusions. So the pessimistic thing that I hope I convinced you about, that there is no sound method at the moment to report the gate fidelities in the way that it's been reported. It's a bit over-optimistic. So we propose the complete and sound method, and it does not require spam calibration. And I would put a question mark here still, whether it's practical. We have to learn how it scales to a large number of qubits. Technical results that I would argue is that robust certification of the S-gate model, and that we don't need to assume what kind of crosstalk you have, so you build the addressability of qubits inside. Now, what's an outlook here? Of course, we need to prove the robustness, and that's not easy. I think some of you have seen this talk before. We are trying. Trust us, we are trying to do this. It's easier to do numerics. Experimentalist tells us, oh, who cares about the actual proofs? If you have numerics, that's good enough. But we do want to get this done. And what's more important for the experimental perspective, we also want to separate spam for the gate errors. And here we want to use already well-established methods where you test the longer sequences or combination of the sequences, and you notice that your probability of failure, if it doesn't increase with the depth of the whole circuit, then you can learn that probably the errors came from the state preparation and measurement. So we want to build on the existing literature, but do it in the sound way. Yeah. I would like to thank you for your attention, and I'm happy to get any criticism. And I want to thank Martin, Jan, Nikolai, Lucas, and Anna from my group for the most of the work for this talk. Thank you.
Are there any questions, comments?
Yes.
So what is special about the S-gate? Why do you use the S-gate for this first or final stage? Some gate where u to the 3 was identity or u to the 7 was the identity. Why is it?
So you need a dimension advantage. And this gate gives you a direct, so if you ask what is the classical, so this simplest test that you're looking at, what is the classical model which will solve you that problem, you need 3 classical states. If you make the test longer, you will need 4 classical states. For the odd cases, you don't have, it's just prime numbers and counting, you don't have that advantage. But of course, now you can try to generalize it to QDITs. We are also doing it. We have a master's project on that. It gets trickier. It's just prime numbers, the way you count, and then dimension advantage that comes in, and that advantage itself gets trickier. S-gate itself is just interesting because actually, once we found this test, we found all this quantum finite state automata literature, which have already studied such advantages in many more cases, but they always go through the square root of z-gate or fourth root of z-gate or so on and so forth, where dimension gets actually exponential.
Do you have any candidates for 2-qubit gates for this?
Yes, yeah. So you can, so we have, so quizzes get much more convoluted. That's why I don't show it on the slide, but you can have it for arbitrary gates pretty much. So we have for all the universal gates. So you can have it for Clifford circuit. What's trickier there, which I didn't think it would work, but then Jan made it work, and then in the hindsight, it was clear that it would work out, how to make these things deterministic. Because as soon as you have the entangling gate, then you worry that you have to estimate probabilities. Yeah. But you can change the basis and show that it still works. So you can come up with a promise problem, which is deterministic, and the only way you can win it is with the entangling gate and the separation. This you can show.
Thanks. That's very interesting. Thank you.
More questions? Right, if not, let's thank Mariam again.